Hello everyone, I'm Bivan. I'm very excited to share my ICCV work, PRVQL, Progressive Knowledge-guided Refinement for robust egocentric vision query localization. And this is the GitHub. It includes the code and model in here. If you find it useful, please give our a star. First, let's go to the outline of my presentation. It includes the background, motivation, method, experiment, and the conclusion. In the background, first I want to introduce the VQL task. This task is belong to the episodic memory benchmark. And this task is aimed to answer the question, where did I last see an object X? Specifically, it's given a long-form egocentric video. This video presents the past experience and recorded from a human via camera. The goal of the task is to search and localize a vision query object, and the application of the task is AI assistant engine and robotics. In here, the task can divide to two parts. First is spatial localization. In each frame, it needs to give a bounding box to locate the spatial position of the target. And second is the temporal localization. It needs to localize the frame of the appearance in the whole video. Usually this video is about 1000 frames, and the target is very short. Usually 30 minutes. 30 seconds, so it's very short. Next, let's go to the dataset. This dataset is EgoVQL dataset. We use this dataset in the task. It's a very large-scale egocentric video dataset. It's only designed for the first-person video, and it covers many worldwide locations and many countries, include a lot of daily life activity in this video. Now let's go to the motivation. In the motivation, I want to compare the existing EgoVQL method with our proposal PRVQL. In this illustration, the input visual query and egocentric video. About the existing method, it's usually an end-to-end model to make this input to get the output. And how about our proposal VQL? Our VQL uses a multi-stage to get the knowledge from the video and use this knowledge to refine in the next stage. And finally, we will get a more accurate localization because we learning the knowledge from the video, not only from the query. Well, let's go to the overview of our method. In here, the input is egocentric video and visual query. First is using a backbone here to get the video feature V1 and query feature Q1. And then we will use mailing stage. Each stage will output the update feature, video feature V2 and query feature Q2. And each feature and this update feature will use in the next stage to make a more accurate localization. And then after stage K, we will input the output. The output will input to a spatial temporal predict to get the final result. Well, this is a detail about the appearance knowledge generation. This module is armed to extract the discriminative appearance curl of the target. In here, the input video feature and query feature input to this stage, and the video feature will first input to a self-attention block, and then use a downsampling, and then combine the position embedding to input to a mask self-attention block. Then we'll get the feature H1. This feature and the video feature B1 will input to the AKG. This is the detail of the AKG. The HK will input and divide to two parts. These two parts, finally, these two parts will get the C bar K and B bar K. The C bar K is the scroll of each frame, and the B bar K is the bounding box of each frame. And then using a sampling to get the BK. And this BK, we will choose the top N operation here. Choose the top N here, and this top N will get we'll use the RA lane with the video feature to get the appearance knowledge here. Well, this is the visualization of the AKG. In here, we can see the query, and this is the target appearance knowledge. In our work, we choose the top K, the K equals 3, so we get the top 3 here. This is the query, and this is the top 3 in the video of the object. And then we will extract their feature and combine with the query to get a new feature. And that new feature will be used in the next stage of the input. Well, let's go to the second module, the spatial knowledge generation. This module is the goal of this module is to enhance the spatial focus on the target within the video feature. The TK and SK is two attention map. The two attention map input. The TK is from the cross attention block, and the SK is from the self attention block. And these two feature map. First, let's look at this. This feature map will extract this feature. This feature will extract and then using upsample to get the same size of this one, and then combine these two to get a new attention weight. This weight will be using on the video. In here, I give a visualization of this is the query, and this is the KK here, KKS here. The spatial curve. You can see it's the attention weight is in the target here, and we will use this attention map to help our model to focus more on the target and discard the noise in the background. Well, this is the experience of our method. First, we compare our method with other in the Ego4D. This table is about the visualization set, and this table is about the data set, test set. In these two sets, we can see our method gets the best performer in all metrics compared with others. let's go to the ablation study. First is about the AKG and SKG. AKG is contribute more than SKG. In here, in this lane 2 and lane 3. Lane 2 is only use AKG, and lane 3 is only use SKG. We can see only use AKG get a high result than only use SKG. And if we use both, we will get the best performer. This is a visualization, the query, visual query, and when we use the refinement, we can see, this is a without refinement. When without refinement, we can see this is the red bounding box is the ground truth, and this is the attention map. We can see the attention. It's difficult to locate the target, and if we use the refinement, progressive refinement, we can see the attention is always on the target. So it means that if we use the refinement, you add these two modules, AKG and SKG, we will get a more better result. Well, let's go to the second ablation study. It's about the number of stage. In here, we use the stage 1, 2, 3, 4, and then we find only use the stage 3, we get the best performer here. We find that if we use stage 4, if we use 4 stage, the performer it will degradation. We think that's because it will introduce some noise about from the video, not the target, from the background of the video. Well, let's go to the second ablation study. It's on the number of target boxes in AKG. In here, we use n equal 2, 3, 4, 5, and then we can see we use 3, we get the best performer. In here, this metric, the STAP, is the main metric of our task. And when n equals 3 in the STAP recover and success, get the best performer. So finally, we use the n equals 3 in here. This is the example, the query and the top 3 from the video. This is the last ablation study. It's on the RY feature size. We choose 3, 5, 7, 9, 4 sides, and then we find use the 5x5, we get the best performer. This is the AKG module, and in here, in the last layer, we use the RY line here. This is the top 3 bounding box, and this is the video feature. Use the RY line to get the feature of the appearance of these three bounding box feature, and this feature we called appearance knowledge feature. In here, we compare the method in different scale in the video. We have 3 scales: small, middle, and large. And we can see this table. When use the small scale, the coconformer gets the first place. Just because the coconformer is use the original resolution of the frame, but our method and VKLC is using a low resolution. So in the small scale, the co-conformer gets the best performer. In the middle and the large scale, our proposal gets the best performer. This is a visualization of our method. You can see the blue is the VQLC, the red box is our proposal, the gray is the ground truth. You can see here always the red our proposal and the gray ground truth here and here. Also in here we can see our method, the red box can locate his, but the blue one, it's will make some mistake. For example, this is a window. It detects this as a target. This is a visualization about the temporal detection. In here, this is the whole video, and the gray cover is the ground truth. The red one is the output of our model, and the highlight point is the last appearance. We can see our method can get a good performer. Also, I give a video demo about our method and the VQLC. The yellow bounding box, this one is the ground truth, is a query, and the red box is the proposal. The blue is the VQLC, and the green is the ground truth. Okay, let's go. This is the conclusion of our work, VQLC. First, we propose a novel multi-stage framework for robust visual query localization, and it includes two parts. First is AKG, appearance knowledge generation, and the second is SKG, the spatial knowledge generation. And the target knowledge from each stage guide refinement in the next, and we'll get the result in better accuracy by enhanced query and video feature. As a result, we achieve the SOTA performer in EgoVQL dataset. In the future work, we will consider the segment anything tool. This is a pre-trained vision model, and it gets very good in segmentation in video. So I think it can use in our task, in the VQL task, can get a more accuracy result.